Hello, everyone. Welcome to third session of quantitative data analysis workshop. So today we are going to talk about some of the statistical techniques which you can use for your hypothesis testing. Predominantly, we are going to talk about that how can you compare mean scores across different categories. And then we are going to talk about regression analysis. And while we'll be talking about the mean comparison part, we will also talk about ANOVA. So these are the three techniques which we are going to talk about today. And towards the end of the session, on last slide, I'll show you a roadmap regarding different decision points in your statistical data analysis. So, for example, what type of variables, if you have X variable of this nature and Y variable of this nature, what statistical technique is most suitable for that kind of analysis and things like that. Okay, so we'll talk about comparison of means, and in comparison of means, we'll talk about independent sample Ttest and ANOVA, and then linear regression. And very briefly, we will touch upon the correlations part because we already talked about this in the last two sessions. Okay, so when it comes to the hypothesis testing, we look at, so whenever you run a statistical technique, no matter whether it's ANOVA, Ttest, Ftest, regression, the SPSS would give you certain statistics in the output. Now, some of the statistics which are relevant to you, you would look at those statistics. But again, as I explained in earlier sessions, that looking at those statistics in isolation is not sufficient. Rather, we are concerned with the term statistical significance, that whether those statistics are statistically significant or not. And for that, we have to go back to the p-value. So the p-value would tell us that this statistic, which SPSS is giving us as a part of the output, whether that's statistically significant or not. If that number is statistically significant, only then we would go ahead and we would interpret that. If that is not statistically significant, which means that our null hypothesis is not supported. Our alternate hypothesis, our main hypothesis is not supported. So from that concept, we already talked about that we typically look at the p-value which is less than 0.05. Now, when I say the p-value less than 0.05, that means that, which means that we are talking here a confidence interval of 95%, that we can say with 95% surety, or there's a 95% probability that the statistic which we are getting, that statistic is going to hold in the general population. Because in statistics, we deal with sample and we try to generalize it to the population. And whether that generalization holds or not, that depends on the probability, which is here denoted by p-value. Sometimes you would see that people talk about 99% confidence interval, which means a p-value of 0.01. But in most of the cases, in 99% of the cases, we take a p-value less than 0.05, which means 95% confidence interval. Okay, so these are the two things which we are concerned with when we look at the output of our statistical tests which we are running in SPSS. Okay, correlation, we already talked about this, that the possible values are between 1 and -1. And basically, this tells us the association between two scale variables, the Pearson correlations. And obviously we have to look at the p-value, that whether that correlation is significant or not, statistically significant or not. And if it's just statistically significant, only then we interpret it. If it is statistically non-significant, we don't interpret it. Okay. Now, comparison of means. For example, let's take the example of the data set we have been playing with, this sleep 3D file. For instance, you are interested in knowing that are there any differences, statistically significant differences on height across males and females. Now, if this is your research question, that you want to see that whether men and women, they are statistically different on the height variable. Now, if this is your research question, then we would run a t-test to answer this question. Now, basically, here we are talking about comparison of means. We will see that whether the mean score of females on height variable and the mean score of height of males and the mean score of height of females, what are those mean scores? And if we get the mean score, we say, okay, maybe one for male, the mean score is on height is maybe 5 feet, okay? And for females, it's maybe 5 feet, 5 inches, 5.5 feet. Now, the next question comes again that whether these differences, so we can see a difference here because both means are different. We would see that whether these means are statistically significantly different from each other or not. So for that purpose, we run a t-test, which gives us a t-statistic and a corresponding p-value. And if the p-value is less than 0.05, we would say that there are mean differences between two groups. Now, in SPSS, there are different types of t-tests. Predominantly, there are two types of t-tests which we deal with. One is independent sample t-test, and the second one is dependent sample or repeated Meyer t-test. Now, independent sample t-test means that you are testing two groups at one point in time. Now, for example, just take this example of a male and female, which we just discussed. Now, basically, we have two groups. One is male and one is female. And we are testing them on which variable? On height variable, but at one point in time. So we have two groups and we are testing them on one of the variables of our interest, that is height. So in that case, this design would be an independent sample t-test design. And we will use independent t-test to see that are there any significant mean differences on height between male and female groups. We also call it the between group design as well. Now, the second type is within group or repeated Meyer design. Now, within group or repeated Meyer or dependent sample t-test, we test one group at 2 times. Now, for example, if like the participants who registered for this workshop, let's consider those a group. And before we start our first session, I took a quiz, a few people on your quantitative analysis skills. So each one of you would get a score. Let's suppose the quiz was of 50 marks. So each one of you will get a score out of 50. Now, at the end of the workshop, after 3 days, I took another test and I again test your knowledge about quantitative skills. Now, again, each one of you will get some marks out of 50. Now I can compare, so you are the same group and I can compare your scores before this workshop and after this workshop to see that are there any significant differences, which means This way I can also test that whether this workshop is of any use to you people or not. So this design is because you are the same group. It is a repeated measure design because I'm repeating my measure before the workshop and at the end of the workshop. And we also called it within group design or dependent sample t-test. So now we have the same group which has been tested twice. So this type of design, we call it dependent sample t-test, or people have been using different terms like related t-test, paired sample t-test. So it's the same thing. So now you got the difference that when you have to use independent sample t-test and when you have to use dependent sample t-test, or the other names you can see on this slide: between group versus within group, independent design versus repeated measure design, and independent t-test versus dependent or related t-test. We can also use, this type of statistical, this t-test for experimental designs. Now, experimental design, it's more or less the experimental design which I just explained you, that if I before any intervention, if I see your quantitative skills knowledge before this workshop, and at the end again if this is my problem, that if this is my research problem, that whether this workshop is enhancing your knowledge or not, so I can do like this. Similarly, for example, the administration of different drugs. For example, nowadays we are talking about COVID. So if you are talking about the effectiveness of a vaccine, what you can do, you can have two groups, one group which has been administered with vaccine, and the second group which has not been administered with vaccine. And at the end, maybe you can measure their general health, or whatever you say, the probability, or actual conditions, that whether you have got COVID or not. And then you can run t-test to see that are there any significant differences on your variable of interest, which might be health, which might be getting COVID or not, to see that are there any significant differences across these two groups, the group with the control group and the group which has got vaccine. So this is how we use this t-test for experimental design. Now, this t-test is only used when your independent variable is categorical with two categories and dependent variable is a scale variable. So this is the condition. So you will use this test when your independent variable is categorical and dependent variable is a scale. For example, just going back to my earlier example of male and female, and I was interested in knowing that are there any significant differences in heights of male and female. So height is a variable which is a scalar variable, which is my dependent variable, and my independent variable here is a gender, which has two categories, male and female. So if my research question is like this, that my independent variable is a categorical variable with two categories, or you can say the nominal variable, and dependent variable is a scale variable, then I would use a t-test. Now, what's the null hypothesis in t-test? The null hypothesis is there are no mean differences between two groups, and the alternate hypothesis state that there are mean differences between two groups. Now, this means that when you look at your outcome, and if you see that the p-value is less than 0.05, which hypothesis you are going to accept? If p-value is less than 0.05, which hypothesis you are going to accept? H0 or H1? You can write in the chat window if you want. Anyone who would like to answer? Yes, H1. If p-value is significant, which means if p-value is less than 0.05, we would always accept H1. Okay. Okay. Now moving on. There are some assumptions of t-test, which means that before running the test, you need to make sure that these assumptions are in place. For example, data should be normal for each group. So as we have two groups like male and female, so the data on our way of our variable of interest, which is scale variable height, that should be normal or close to normality. Independence of scores. Now, independence of scores means, now this is the assumption for independent t-test, which means both groups they do not have interference across each other while you are measuring that particular variable. Homogeneity of variance. Now, homogeneity of variance is again an assumption of independent t-test. Homogeneity of variance means that data in both groups are distributed homogeneously across around the mean. So the both groups, the data spread should be same. Now, once you run the t-test, SPSS would give you an output related to Levin's test. Now we use Levin's test to see that whether the variances of the group are equal or not. So H naught here is the variances of the groups are equal, and HA or H1 says the variances of the groups are not equal. These are the hypotheses for Levin's test, which means if you have a p-value which is less than 0.05 for this test, you would say, which means if p is less than 0.05, it means you are going to accept HA, and the HA says the variances of the groups are not equal. If p is greater than 0.05, then you would accept H naught, and the H naught says the variances of the groups are equal. So you see here, like we are not talking about that the p should be less than 0.05, rather here we are talking about that if the variances of the groups are equal, then the p here should be greater than 0.05, because if p is greater than 0.05, you would accept your H naught, and H naught says that variances of the groups are equal. Okay, so moving on. Now let's suppose that this is our alternate hypothesis that males have greater weight than females. So now how we can test that? So this is what I'm going to do now. Now this is our hypothesis which we are interested in. We have hypothesized that males have greater weight than females in our sample size. So what I will do, this is my data file. I will go to transform, I will go to analyze. In analyze, if I go down here, I will find this compare means. Now in compare means, you have different options. You have like one sample t-test, independent sample t-test, paired sample t-test, one-way ANOVA. Now, because here I have two distinct groups, males and females, so I'm going to choose independent sample t-test, because both groups are different and both groups are measured at one point in time. If I had the same group and that was measured at 2 times, then I would have used paired sample t-test. So I would use this independent sample t-test. I would click here. Okay. Now let me move this back so that we can. Okay. Now test variable here is my dependent variable. Now our hypotheses say that we are interested in knowing that males have greater weight than females. So weight is my dependent variables, and my independent variable is a gender having 2 categories, males and females. So I'll put in weight and gender. So test variable is weight. I'll put weight here. And grouping variable is my independent variable, which is gender. So this is this variable sex. I'll put sex here. Now you see like 2 question marks in this bracket. So I'll click on the define group and I would define it. Now what is group 1? So for example, let me just go back and see. If we go here to the variable view, you can see if we can see like, okay, so we have not defined the values. But for example, if you go to the data view, the sex is 0 and 0 and 1. It has been coded 0 and 1. So 0 is male and 1 is female. So I would define it. So you can just note it down that 0 is male and 1 is female. So my group 1 here is 0 and group 2 is 1. So I'll just have to put 0 and 1 here. I'll say continue. Once I click continue, you will find the question marks are being replaced by 0 and 1. Now, if you go to the options, there's nothing, specific here. So you'll just click continue and you will click OK. So when you click OK, SPSS would give you this output. Now, if you look at the output, in the first table here, you have weight of the respondents in kg, and then you have two groups, 0 and 1. Now, 0 is the mean of the 0 group is, I think I got it wrong. So 0 is basically female and 1 is male. Okay, let's take it this way. So 0 is female and 1 is male. So the 0 group has a mean weight of 66.09 and the 0 group here is female. So female has a weight of 66.09. The male group, which is represented by 1, has a mean weight of 82.45. Okay? And these are the standard deviations of each group. Now, if you just look at these two means are different from each other. And you can see that the group number 1, which is male, that has a higher weight as compared to female. But we cannot be sure, we cannot claim this until and unless we look at what? Anyone? By looking at these two mean values, can we claim that these two means are statistically different? If we only look at this table, first table. My question is, do you think that when we look at the mean, the females have an average weight of 66 kilo and males have an average weight of 82 kilo? Now these two means are different from each other. This mean is 82.45. This is 66.09. Yes, exactly. Thank you, Dr. Azam. So we cannot claim or we cannot say that these means are significantly different from each other until and unless we look at the p-value. So we go down here to the second table. If you go to the second table, we talked about the Levin's test. Now Levin test check for homogeneity of variances of the both groups. Now, if you look at the statistics of the Levin test, now here you get the F value. Now this F value is for Levin's test, which is 0.20, and the significance level is 0.649. Now, do you think that the variances of both groups are equal or not equal? Go to the slides which we just talked about. Okay, let me open the slides here as well. Shows the slide and sorry. Yeah. Now you can see that my H0 was the variances of the groups are equal, and my alternate hypothesis, the variance of the groups are not equal. And when I look at my Levin's test output, this is what I'm getting, that is 0.208 and significance value is 649. Okay, Mahana is saying that these are equal. Why these are equal? Because which hypothesis we are going to accept here, H0 or HA? Yes, we would accept H0 or null hypothesis because P is greater than, excellent, P is greater than 0.05. And our H0 says that the variances of the groups are equal. So we can say that the variances of the groups are equal because the p-value is greater than 0.05. Okay, now I'll go back to the output again. Sorry. Okay, so this means now here you have two rows. The first one is equal variances assumed and the second one is equal variances not assumed. So which row we are going to interpret, the first row or the second row? The question is, because in both rows the first row. Yes, exactly the first row, because we are assuming that the variances across both groups are equal. Okay, so if we interpret the first row, this is the t statistic which t-test is giving us, which is minus 9.9. So no need to, look at it. You would go and now, for instance, we would see a mean difference of minus 16.364. And this is what mean difference is, because if you subtract, first group means minus second group mean, you would get this value minus 16.34. Like, for example, if you do the math, 66.09 minus 82.45, which means that the average weight of females minus the average weight of females, you will get this mean difference, which is minus 16.364. Now, the next question, whether that mean is statistically different or not, you can look at the significance value here, significance two-tailed, which is 0.000. Now here, the p-value is less than 0.0001 even, So, or just let's take this cutoff of 0.05. So p-value here is less than 0.05. So what do you think? Now, again, let me open the slides and now H0 says that, I'll try to drag it to the other side, the slides. Oops. No worries. So H0 here says there are no mean differences between two groups, and H1 says there are mean differences between two groups. Now your p-value of these statistics, your p-value here, the t statistics is 0.000, which means which is less than 0.05. Now in this case, we are going to accept the alternate hypothesis, which says that there are mean differences across two groups. Right? Okay, so coming back to the slides, that how do we report such results? We write like this, that on average, males have greater weight, M is equal to 82.45. We also report the standard error. This is how we do. SE is equal to 1.30. You have it in your SPSS table. Then females, M is 66.09. Standard error is 1.04. And then you report the Ttest. Now in the bracket here, this is degrees of freedom, DF. Now if you, I'm trying to move this away so that you can see it, but yeah. So here you can see DF, which are 247. So we write this 247 here. And then the second thing you write is the T statistics, which is minus 9.9. And of course, the P is less than 0.05. So this is how we report the results, that on average, males have greater weight, M is equal to 82.45, standard error 1.3, then females, their mean score 60.09, standard this, T247, this is degrees of freedom, okay, 247, T is equal to minus 9.9 T statistics, and of course the P value. Okay, so our hypothesis in this case is spotted, because we have found that males have greater weight than females, and that difference is statistically significant. Okay, any question? Okay, great. Okay, so moving on. Oops. Now, what if we have more than 2 categories? Now, Ttest was concerned that when we have only 2 categories in our independent variable, like male and female, dead or alive, or old and young. Now, if you have more than 2 categories, you cannot use Ttest, rather you will use ANOVA. ANOVA stands for analysis of variance. AN is analysis, O is off, and VA is variance. So analysis of variance. If your independent variable has more than 2 categories, then we will use ANOVA. Now, ANOVA gives you an F statistics, which is similar to a T statistics. ANOVA also has the same assumptions which the Ttest had. Basically, what ANOVA does, ANOVA runs series of T-tests between two groups. So that's why more or less it has the same assumptions, like normality of data for each group, homogeneity of variance, and independence of observations. Okay, now whenever you run ANOVA, you will get an F statistic. If the F test is significant, this tells us that one or more than one combination of your different categories in your data set, their differences are significant. But F test does not tell you that which combination has a significant mean difference. So in order to explore it further, you have to run certain post hoc tests. Now, there are 2 ways of going about it. If you have specific hypothesis in advance, a priori theoretical argument that these 2 groups would differ on a specific variable, which is a variable of your interest, then you will use comparison or contrasts. Now, we are not going to cover this in this session, but I have mentioned the page. You can find the details on page 801, section 12.4 of Andy Field's book. It's very well explained there. So you have to assign weights to different categories, and so in order to compare 2 specific categories on which you have about which you have made your hypothesis. But if you are just interested in exploratory analysis and you want to see that which 2 groups differ from each other on a specific variable, you would do post hoc comparisons. Now, we have different tests available in SPSS which help us to do the post hoc comparisons between 2 groups. More or less, you get the same results from those tests, but some of the tests are sensitive to certain assumptions, Assumptions like, homogeneity of variance, assumptions that your groups are of equal size, assumption that your data is normal, and things like that. So keeping in view the characteristics of your data, you can choose a specific test. For example, again, as I just mentioned, that postdoc tests are used when there are no specific hypotheses. And our interest here is to compare two groups, and we are interested in explanatory analysis. Again, the choice of postdoc test, a specific postdoc test, that depends on that does the test control type 1 error, does the test control type 2 error. If you remember yesterday, we talked about the errors. We discussed that type 1 error is when you reject H naught actually when it is true, which means like you end up in getting a false positive result. And type 2 error is when you get a false negative result, which means you accept H naught actually when it is false in the population. Okay, and also if the assumption of ANOVA are violated, which tests are most reliable? Now, these are different tests which you find in SPSS, and against each test, you can find a decision criteria to use this test. For example, Bonferroni's test, this is test which control type 1 error, and it is more powerful when number of groups are small. Okay, for example, if you're dealing with like 4 or 5 groups up to 5, this is fine. If you have a bigger number of groups, then probably Bonferroni is not a good choice. And this is also used when variance among groups is homogeneous. Tukey's, now this also controls type 1 error. This is more or less, same. It also uses the same assumption that when variance among groups is homogeneous, but it is more powerful when number of groups are large. So if you have a large group, more than 4 or even 5, then Tukey's maybe is more reliable than Bonferroni's. REWQ, again, that controls type 1 error, and it is more powerful, but it should not be used when there are different group sizes. For example, if you are dealing with 3 groups or 3 categories in your independent variable, and in one category you have sample size of 20, in the other you have a sample size of maybe 150, and in the third you have a sample size of 50. So you see that you have very like different numbers of respondents under each category. So in that case, this is not recommended. And this is also used when variance among groups is homogeneous. And then you have Hodgeberg's GT2. This is used when you have different sample size across groups and when variance is homogeneous. And then you have Gabriel's, again, different sample size across groups, but should not be used when sample sizes are very different. And again, it assumes that homogeneous is homogeneous. The last 2 tests which are mentioned here on the slide assume that the variance across groups is non-homogeneous. So if the variance is non-homogeneous, we typically look at Donut C and Games Howell. So when you are running these tests, you can ask SPSS to give you output on each one of these, and then sometimes even you can compare and contrast that how the output looks under each test. Okay, now for example, this is a question which we are interested in exploring. Are there significant differences in current weight across different marital status groups? Now, what's the dependent variable here? Yeah, anyone? What's my dependent variable here in this question? Okay, excellent. So weight is my dependent variable, and what's my independent variable? marital status. Okay. And so we'll just go to our data file and see that what type of technique we are going to use. Okay, for instance, if we go here to the variable view and we look at the marital status, this is the variable. Now, how many categories marital status has? The marital status has 4 categories. So do you think I can use the Ttest here? Which technique should I use, ANOVA or Ttest? ANOVA. Why do you think that we should use ANOVA? Why not Ttest? Anyone? Yes, because this independent variable has more than 2 categories. If like this variable had only 2 categories like single and married, I could have used Ttest. But now categories are more than 2, where we have single, married, divorced, widowed. So we cannot use Ttest. So we have to use ANOVA. Okay, fine. So what we'll do, we will just click here on analyze. In analyze, we will again go down to compare means. In compare means, we would go down to one-way ANOVA. Okay. So if I click here on one-way ANOVA, okay, let me put this back so that we are able to do it from beginning. Okay, so this is my dependent list and this is my independent list. Okay, because in ANOVA you will have only one independent variable, and in this case our independent variable is marital status. So I'll just click on the marital status and I'll bring in here, and in my dependent list, because I was interested in okay, let me go back to my slide to see current weight. Okay, so this is my current weight. I'll put in here. Okay. What if you have more than one independent variable here and categorical? For example, if we are interested in knowing that do the current weight varies across marital status and another education level, which also has like more than 2 categories, and we also want to see the interaction between like the marital status and education level. Now in that case we cannot use one-way ANOVA, because one-way ANOVA, you can see here, this box is only for one variable. So one-way ANOVA, one independent, and you can have multiple dependent variables, but that will be done one by one. But the dependent has to be one. Now, in that case, if you have more than one independent variable, categorical independent variable, we will use MANOVA. Not ANOVA, rather MANOVA. And MANOVA, for instance, you will go to analyze, then you will go to here, general linear models, and general linear model, you will go to multivariate. So this is how you will use it from here. But we're not going to talk about in this session, but I'm just, this just comes to my mind and I thought I should tell you that if you have one independent variable, categorical independent variable, you will use ANOVA. If you have more than one independent variable with more than 2 categories, you will use MANOVA, and MANOVA is here like general linear model, GLM, and multivariate. Okay, so if you click here on the contrasts, now we are not going to use contrasts here because I told you that contrasts is used when you have specific hypothesis, when you have a priori expectations. So we are not going to use it here, but if you're interested in using it, you have certain type of hypothesis, you can consult the page number 802 of Andy Field's book. So now if you click here on the post hoc, now this would give me some options. Now you can see that there are certain tests, a list of tests, which are arranged in two boxes. The first one is equal variances assumed, and the second one is equal variances not assumed. You remember that in equal variances assumed, we talked about Bonferroni, we talked about Tukey's, we talked about this REGWQ. We also talked about Hochberg's GT2, it's here, and we also talked about Gabriel's. And in equal variances not assumed, we talked about Donut C and Games Howell. So I checked all of these. There is no problem in that. Now, similarly, you can also ask the SPSS here to set the significance level. So the minimum is 0.05, which is default. But if you want to set it to 0.01, you can still do that. If you want to set it to 0.001, you can still do that. Now, SPSS would flag all those values which are statistically significant. Or if I press continue, and if I press, okay, if you go to options, there isn't much in the option. But if you're interested in getting the descriptive statistics of your variable, you can check that. And there are a couple of other options like homogeneity of variance test, that Levin's test. Okay, let's ask SPSS to, give output on homogeneity of variance, and click continue. And if I click on OK, so let me delete the first part. Now, if you look here, you can see the test of homogeneity of variances. And we take this first line, which is based on the mean. If you look at the p-value is 0.26, which is not significant. And when p-value is not significant, we accept the null hypothesis. And in this case, Levin statistics case, our null hypothesis was that the groups have homogeneous variances or equal variances. So in that case, we are sure now here that variances of different groups, the four groups which we have under this variable marital status, those are homogeneous. So we are going to look at the output of the tests which are used for homogeneity of variances, like Bonferroni, Tukey's, REGWQ, Hochberg's GT2, and Gabriel's. Okay, you can also look here. If you go down, you will get this F statistic. Now, first thing you are going to look at is the F statistic. Now, if this F statistic is not significant, we will not go ahead in interpreting this post-hoc test table. So this is the first step. If it is not significant, halas, we will just say that there are no significant differences on current weight across different groups of marital status. But now here we can see that this is significant. This is like less than 0.05, like 0.02, and F value of F is 3.26. So we can say that there are significant differences across groups on current weight. Now the next question comes, which of those groups are different from each other? So in order to answer that, we will go down to the post-hoc table where multiple comparison has been done. Now we will just take, for example, because we have a homogeneous variances, or so let's look at any of these. Okay, Tukey's. If you look at the output, now here you will have this I marital status and J marital status. So the marital status of single is compared, the mean of the marital status of those who are single are compared with those who are married. Okay, and then the comparison, mean comparison of single with divorced, mean comparison of single with widowed. So you will see that each category is compared against the other three categories. Now, for instance, if you look here, the first row, the mean difference I minus j is minus 0.616. Now, this means because the result is in a minus, which means that the married, they have a higher weight. They have a higher mean. And I, which is single, they have a lower mean. And that's why you end up in getting a minus with your answer. So, and you can see that this is flagged. There is a star on top of that, static. And this is significant. It's 0.021. So this difference is significant at p-value less than 0.05. So we can say that there are significant differences on on weight between single and married, where who have a higher weight here, married or single? Yes, married. So the married have, so the mean differences between married and single are significant, where married have a higher weight than single. Now, if you go further up in the row, you see that significant value is 0.021. And another way of doing this is, if you go to this last two column, you have lower bound and upper bound of confidence interval. Now, your p-value would always be significant if the confidence interval does not contain a zero. Now, for example, which means you are not crossing the origin, you are not, going from minus to plus or plus to minus. So if both lower bound and the upper bound, they have the same, signs, this means that your p-value is significant. That's why you can see that this is minus 1.1 and minus 0.07, both minus, and that's why you end up in having a significant p-value. If you look at the second row, you see that minus 1.06 and 0.76. So this confidence interval contain a zero, and that's why you see a non-significant p-value, which is 0.973. Now, apart from this group, single and married, we don't see any other difference. If I just go down this this column, the significance column, this is 0.021. This is the same married single 0.021. If you go down further down again, so till here. So you can see that only the two groups, they are different from each other as far as their weight is concerned, and these two groups are married and single, where married have a higher weight as compared to single. Okay, that's it. Any other question? So you can just interpret one of these tests, because I just, for demonstration purposes, I clicked so many, but if you know in advance that whether the variances are homogeneous or not, you can select few. But there's no harm in getting all of those, and then you can report just one of those. If you look that more or less all the tests are pointing in the same direction. Tukis are giving us the same result. Bonferroni is the same. Gabriel is same. Hochberg is same. Even the difference is same. Games Oval is the same. Unit C is same. Yeah. Okay. So this is how you do ANOVA. I hope it's clear. Okay. So going back to what's the answer to this question? Answer to this question is yes, there are significant differences across two groups, between two groups, which are single and married, where married have a higher weight as compared to single. Okay. So this is the last thing for today's session, which is the linear regression. Now, linear regression is used when both our independent and dependent variable are scale variables. Basically, a regression tests causality. If A leads to B, or if A predicts B. Now, these kinds of hypotheses, where you have a true dependent variable, we use regression. Our regression has certain assumptions. It has assumption of normality. Your data should be normal. It has assumption of linearity, that there should be a linear relationship, not an exponential or inverse relationship between the two variables you are interested in. And your data should not suffer from multicollinearity. Now, what is multicollinearity? Multicollinearity is a high correlation among your independent variables. For example, in regression, you have one dependent variable and you can have more than one independent variables. But if those independent variables are highly correlated, then it's not good, which means you have to drop one of them, so that you don't end up in having a multicollinearity in your data. And there are tests which you can do to see that whether your data is suffering from multicollinearity or not. And of course, the independence of observations, which means that one case is observation on one of your respondents are not being influenced by other respondents. Okay, now for example, this is our model which we want to test. We have 4 hypotheses. We are saying that age negatively predicts physical fitness, energy level positively predicts physical fitness, alcoholic drinks negatively predicts physical fitness, and sleep hours positively predict physical fitness. Now, if I look at the nature of my variables, I have 4 independent variables, which are scale variables. They have a continuous measurement, and I have 1 dependent variable, which is again, a scale variable. Now, in that case, I would use regression. Now, let me go back. Okay. So I'll demonstrate that how we can use that. Once you run the regression, one of the important things which typically we look at is a tolerance value and VIF, variance inflation factor. If the tolerance value is less than 0.1 and VIF is greater than 10, now that is an indicative of multicollinearity in your data, which means that now you have to drop one of the variables to reduce the multicollinearity, or the factors or the independent factors which you have hypothesized are redundant, are related to each other. So this is something which people take it very seriously, multicollinearity issue. So you have to check this. The second thing we typically look at is the F value. Now, just like the ANOVA, if the F value is significant, we move on to the interpretation part. But if value is not significant, we stop it there and we say that our regression model is not, is not good enough, that where our independent factors are predicting the dependent factor. Another thing which we typically look at is R-square value. Now, R-square value tells us the explanatory power of your theoretical model. Now, basically, R-square tells you the proportion of variance which has been in the dependent variable, which has been explained by independent variables in your regression model. Now, for example, if I go back to this previous slide, physical fitness is my dependent variable and these 4 are my independent variables. Now, R-square value for this model would tell you that the variance in physical fitness, how much of that variance is being captured by these 4 factors. Now, if we have a low variance which is being captured by these 4 factors, which means that there are some other factors which we have not taken into account, which can explain the variation in physical fitness. Or maybe our arguments or our theory is not strong enough to explain all the variation in physical fitness, or our data is not supporting our theory, which we hypothesized that these 5 factors predict physical fitness. So if you have a lower R-square value, this means that the remaining variance, which is unaccounted for, that might have been explained by some other factors. So you need to take those factors into consideration for your future research. So after looking at the R-square value, we look at the beta coefficients. You remember that in correlation, we use the symbol R. R we use for correlations, and beta we use for regression coefficients. Now, regression S-basis gives you 2 types of beta values. One is the standardized and the other one is the unstandardized. Now, the unstandardized coefficients, you obtain those based on the original measurement scales of the variables. And the standardized beta, basically you obtain from standardized scores. You remember yesterday we calculated the Z-score, standardized scores, where what we did, we did like value minus mean divided by standard dev. So that is the standardized score. So basically S-basis converts scores into standardized scores and then runs the regression. So standardized coefficients are obtained after running a regression model on standardized variables. Now, when we are interpreting how to interpret unstandardized betas, now this is how you will interpret unstandardized beta. A change of 1 unit in the independent variable X is associated with a change of beta units in the outcome variable Y. Now, for example, we will talk about this once we have the regression output. And for standardized beta, we don't use the word unit, rather we will use the word a change of 1 standard deviation in X is associated with a change of beta standard deviations in Y. So this is how, if you are using standardized estimates, this is how you would interpret, and if you are using unstandardized estimates, this is how you're gonna interpret it. Unstandardized betas are usually used in interpreting the individual effect of X and Y. And most of the time in my field, we report unstandardized beta, and we also interpret the unstandardized beta because we are interested in talking about the individual effect of X and Y. But if you are comparing the effect across all your 4, 5, 6, 7, 8, 9, 10, no matter how many independent variables you have, then you can use the standardized estimates. Okay. Now let me go back to the data file. So this was our model. I'll put it here on the side so that we know that what we have to test. Okay, so this is the model we are interested in. Cancel. So let me open the data file. This is data file. Okay. This is the model. Our dependent variable is physical fitness, and independent variable is energy level, age, alcoholic drink, and hours of sleep on weeknights. Okay, so I'll go to analyze. I'll go to you find this here, regression, and after regression I'll click on linear. Okay, let me put this back. Okay. So this is the place for putting in the dependent variable. Now dependent variable here, again, let me open this. Dependent variable here is physical fitness. So I'll drag the physical fitness in there. Where is physical fitness? Fitness is this. And my dependent variables, energy level, age, alcoholic drink, hours of sleep. So Energy level. Yeah, this is the energy level independent. And the second one was age. This is age. Third one was alcoholic drink. How many alcoholic drinks you drink per day? And the fourth one was hours of sleep on weeknights. So this is hours WNIT, okay, weeknights. Okay, so now regression here tells you different methods. Now it has enter, stepwise, move, blah, 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 blah. Now most of the time we do enter. Now enter means that it would enter all the independent variables at one point in time into the regression equation. If I use stepwise, now this will, what it will do, it will enter age, it will give you parameters, and then it would enter the next variable and the third and the fourth. Now in that case, in stepwise, it would give you incremental change in R square when after entering each variable. So if your hypotheses are like this, you are making a comparative effect hypothesis that this variable explain, it has a more explanatory power, then probably you go with this stepwise. But most of the time we go with the default method, which is enter. Now, if you click here on the statistics, I am interested in knowing regression coefficient estimates. Okay, that's fine. I would also like to have the model fit, which is F statistics. I should look at it. And R square change. Now, R square change is very important. Yeah, and then you can also ask SPSS to give you collinearity diagnostics. You know, we talked about the tolerance and the VIF. So click on the continue like this. Okay, now if I click on OK, now this is the output which SPSS would give me. Now, at first place, you will get a model summary. Now you see here, the R square is 0.173, which is 17.3%. Now, what does this mean? What does this 17.3% means? Anyone? I told you a couple of minutes ago. If the R square is 17.3%, what does it mean? Scared mean error of 17%? No. You know, R square tells us that how much variance has been explained by independent variables, how much variance of dependent variable has been explained by your independent variables. Now, which means that only 17% of the variance which we see in our dependent variable has been explained by these four factors like hours sleep per night, energy level, alcoholic drink, and age, which means that almost 73%, not 73, 83% of the variance in my dependent variable is still unexplained, which means that there are a lot of other factors that as well, which impacts our physical fitness. And that's true, isn't it? If we think commonsensically, energy level, age, alcoholic drinks, and sleep hours, that are not the only factors or the main factors which explain the variation in your physical fitness. So that's why we see only a 17% variance being explained by these four factors. Rest of the 83% variations in physical fitness, we don't know. There might be other factors as well. So this tells basically you the explanatory power of your model. Now, higher it is, the better it would be. The higher it is, it means your data fits well your hypothesized relationship. tips. So here you have 17.3%, and but again, you know, as I told you that we cannot look at it in isolation, rather we have to look at the associated p-value. And this R square is significant. It has a p-value of 0.001. So we would go ahead and interpret our individual beta coefficients because this is less than 0.05. Okay, going down, this is an over table, forget about this. Now this is the table which is of interest to you. You can see here in the first column all the predictors for all the independent variables of your model. You have energy level, you have age, you have how many alcoholic drinks per day, and hours sleep per week night. Now here you have unstandardized beta values, okay, and here you have standardized beta values, and then, you know, associated significance. Okay. Okay. Now, for instance, and here you have collinearity values like tolerance and VAF. I told you that what was the cutoff point for, let me go back to slide. What were the cutoff points which I mentioned? If tolerance is less than 0.1 and VAF is greater than 10, then your data is problematic. But here in this case, you can see that none of the VF value is greater than 10. These are close to 1. And none of the tolerance value is less than 0.1. All are greater than 0.1, way above 0.1. So which means that your data is not suffering from multicollinearity. You are good to go. Now we would come back to individual beta coefficient of each predictor and would try to interpret it. Now, if you look at the energy level, and I told you that we would interpret unstandardized values. Now, energy level, the beta coefficient here is minus 0.3, and this is significant because the significance value is 0.000. So minus 0.3 and p value is less than 0.05. So, and if you look at the age is minus 0.001. But if you look at the significance value, it is 0.938. So we forget about it because it is not significant. How many alcoholic drinks per day? 0.02. Significance value is 0.82. We are not going to interpret it. Hours of sleep per week nights. So the beta coefficient for this is 0.23 and significance is 0.10, which is not less than 0.05. So we will not interpret it. So which means that out of the 4 predictors, only one predictor has a significant impact on physical fitness. And that's why you got a low R square value up there, because the explanatory power of your model is weak. Although it's significant, but it's on the low side. 17% variance is being only explained in your dependent variable of physical fitness by these 4 predictors, but out of these 4, 3 do not impact the physical fitness, and there is only one which impacts the physical fitness, and that is energy level. Now, if you look at the value of the energy level, it is minus 0.3, okay, and it is significant. How would we interpret it? If you go back to the slides, you will find the answer. This is how we would interpret it. A change of 1 unit in independent variable. Now, what is your independent variable here is energy level. A change of 1 unit in energy level is associated with a change of minus 0.3 units in the physical fitness. Now, this goes against the common sense. Maybe this is because this is just hypothetical data that we got a negative relationship, which means if energy level is going up, the physical fitness would go down. That's not the case. Usually we think that if energy level is going up, we are more fit. Okay, so this is how you would interpret. So we only found one factor significant. If you look at this output, yeah. and which is energy level minus 0.3, and significance is 0.000. Okay, no need to look at this because these are the details of the collinearity diagnostic. Summaries you have here, you only have to look at tolerance and VIF values. So tolerance should not be less than 0.1 and VIF should not be greater than 10. Okay, so this was about, yes, we always run correlation before regression because we always run descriptive statistics before going to the hypothesis testing part, because regression is hypothesis testing and correlation is, you can see part of usually is it's a part of descriptive statistics. So usually we have, mean, standard deviation and correlation table before we move on to the hypothesis testing part. Okay, one last thing, and then I think we are good to go. Now, this is a flow chart for selecting commonly used statistical tests. Now, for example, a type of data. If you may have two types of data: continuous, which we have been using the term scale as well, scale, or discrete or categorical. So if your data is categorical, now when I say the data, it means that's the only data you have. We would use chi-square test. We have not talked about this, but you can further explore it in Andy Field's book. If your data is continuous and type of question is concerned with the relationship, and if you have a true independent variable here, we will use regression. If you do not have a true independent variable, you don't know which is dependent and which is independent, we will use correlation analysis. And then, again, we have parametric and non-parametric. Parametric tests, usually we use for, we have a large sample size, and those are more robust. Non-parametric tests are those tests which we use when your assumptions are violated to a large extent. For example, your data is not normal. You are, violating the assumption of linearity, multicollinearity, and everything. So you have a very small sample size. So we use non-parametric tests. We didn't talk about this, but there is again a category of non-parametric tests available in SPSS. You can find those in Andy Field's book. So if it's a parametric, we use Pearson's correlation, which we did. Okay. And if your type of question is about the differences, now the next question can come: differences between what? If we are talking about the differences between means, then we will see that how many groups we have. If we have two groups and parameter assumptions are satisfied, we will go for this paired sample t-test or unpaired t-test. And if you have more than two groups and assumptions are satisfied, like normality and homogeneity, we will use ANOVA. And after ANOVA, we will use post-hoc, we will use Tukey's, Bonferroni, we all talked about this. And the other part is non-parametric. If assumptions are not verified, you do transformations. If after transformations, your data fulfill the assumptions, then again, we will go to ANOVA. Else we will use non-parametric tests like Kruskal Valley and things like that. Okay, so this is a general flow chart of what we try to do during these 3 days. Okay, that's all from my side. Thank you very much. And if you have any question, please feel free to ask. Okay, so no question means everything is fine, everything is good. Okay, take care.
Thank you, Dr. Abisari. Thank you very much for this helpful workshop.
Yes, Dr. Azam, this because I updated this PPT today, and this last slide is also part of session 3 PPTs. So you can download these from the shared folder. Shared folder, where is the shared folder? That's a very good question. So I think I did share the link I think I can do it one more time. So for those of you who were not there on the first day, let me do it one more time. And you have all these practice files like assignment question, everything on the share folder, PPT and other stuff as well. Okay. Link. Yeah, here's the link. Here you go. Yes, Sohaib, you were saying something. Sorry, I interrupted you.
No, I was thanking you for this helpful workshop, and thank you for the attendance. And I will add a feedback form so the students can enter the link and fill it. And
Okay.
thank you again, Doctor.
Thank you very much.
We will upload the 3 sessions recordings in the YouTube channel for the College of Graduate Studies within the next few days, inshallah.
Inshallah. Okay. Take care.
Thank you very much.
Bye-bye. Bye-bye.